Next, let's look at continuity and differentiability of inverse functions. So letting f be a function whose domain is an interval I. If f has an inverse function, then the following statements will be true. 1. If f is continuous on its domain, then f inverse is also continuous on its domain. 2. If f is increasing in its domain, then f inverse is increasing on its domain. 3. If f is decreasing, then f inverse is decreasing on their respective domains. And then finally, if f is differentiable at c, and f prime of c is not equal to 0, then f inverse is also differentiable at f of c. Next, let's look at example 4. Derivatives of inverse trigonometric functions. So given that y is equal to the inverse sine of x, they want us to find the derivative of inverse sine. Inverse sine is sometimes also called the arc sine, and so you may see either notation. So since y is equal to the inverse sine of x, that means that the sine of y is equal to x. Now if I differentiate both sides with respect to x, we get d dx sine of y equals d dx of x. And so the derivative of sine of y gives us cosine of y dy dx, differentiating y with respect to x, and the derivative of x is 1. Now we can solve for dy dx by dividing both sides by cosine of y, and so we get dy dx is equal to 1 over the cosine of y. All right, now what is 1 over the cosine of y? So if we look at this triangle given likely by the unit circle, since our hypotenuse is equal to 1, you can see that from the Pythagorean theorem we have the following relationship, where x squared plus cosine of y squared is equal to 1 squared. So x squared plus cosine squared y is equal to 1. And cosine squared y is equal to 1 minus x squared. And so therefore cosine of y is equal to the square root of 1 minus x squared. So that's where that came from. So now that I know what cosine is, we can rewrite this as 1 over the square root of 1 minus x squared. And so this actually is dy dx because now I have an x in it instead of just a y.